Hi everyone. In this video, I'm going to talk about how to think about um, inductive arguments with multiple premises. And we will see we're simply building on what the tools we looked at in the previous lecture where we used Bayes' theorem with multiple conditions. So here's why we might care about inductive arguments with multiple premises. So consider the following argument. Again, imagine you're a researcher studying ravens and you're wondering about their color. So you've observed 10 ravens so far, and they've all been black. And so you conclude from this experiment or these observations that all ravens are black. Now, this kind of inductive argument is called that of generalizing from observed instances. And this is a very, very common type of inductive argument. It's used in everyday life as well as in empirical science. Now, in order to think about how we can capture the inductive strength of this argument, we have to think of this premise as not actually a single premise, but actually a collection of multiple different premises. So you can think of premise P as a conjunction of 10 propositions about each of the ravens you saw. So this conjunction here, B1 and B2 and B3 dot dot dot, all the way to conjoining B10, what this says is that you've seen 10 black ravens. So B1 says the first raven you saw is black, B2 says the second raven you saw is black, and so on for 10 times. And each of these conjuncts, B1 to B10, each of these conjuncts is kind of like a premise in the overall argument. So this argument is kind of an argument with 10 premises, but what we do is we put all the premises together into a single conjunction. So again, in order to understand this argument, it's really kind of an argument with 10 premises, but we've put all the premises together, again, into one big, long conjunction. And now, since we've collected all the premises together into one conjunction, we can determine the strength of the argument by calculating the probability of the conclusion that all ravens are black, given the conjunction P1 and P2, etc. And in this case, it's the conjuncts are about the individual ravens, the 10 ones you've seen. And in general, though, if you're given an argument with a bunch of premises, you can determine the strength of that argument by calculating this conditional probability. You just list out the premises as a big conjunction. And in this case, what we're concerned with, in this case, for this argument, we're concerned with the degree to which the conjunction B1 to B10 confirms the conclusion that all ravens are black. And in fact, we saw how to begin doing this last class where we applied Bayes' theorem to cases where we had multiple conditions. So let's see how to do this. Not where we have two conjuncts, but a really arbitrarily long conjunction. So in order to intuitively get a grasp on what we're going to do, you have to think of observing ravens like sampling from an urn. So each raven you see is kind of like a marble. And the population of all ravens in the world is the urn. So when we're making observations, we're kind of sampling from nature's urn. And at first, as researchers, we don't know what nature's urn contains. We don't know what the true proportion of different colors of ravens is. So nature might contain only black ravens in its urn, or it might have ravens of other colors. So before we make any observations, we don't really know what the true composition of nature's urn is, so to speak. And when we see more and more ravens and observe their color, what we can do is we can update our probabilities about what all ravens in nature's urn are like. Just like as we draw more and more marbles randomly from an urn, we can update our probabilities and our belief in what the overall composition is of that urn. Yeah, so as I just said, Just like we see more and more ravens and note their color and use those observations to inform our theory, similarly, we draw more and more marbles from an urn and note their color, and we get more and more confident about the overall distribution of colors of marbles. So suppose we have an urn in front of us, and suppose before drawing from it, we actually only consider two equally likely possibilities. So this is like a case where we imagine a room full of urns where there's only two types of urns, okay? So we're only going to be considering two hypotheses about what the urn is like. Hypothesis A is that the urn contains only black marbles. So all of the marbles in A are black. And not A, or the other hypothesis, is that the urn contains an equal mix of black and white marbles. Now suppose we draw twice randomly from the urn with replacement, and both times the marble is black. So this is a question involving using Bayes' theorem with multiple conditions. So we want to know what is the probability that we're drawing from an A-type urn, given that the first two draws have been black, and furthermore, where we assume the draws are independent because we're drawing with replacement. And we can calculate this with Bayes' theorem as we saw last class. So applying Bayes' theorem, the long version, we get the following equation. And then in order to calculate the probabilities of the evidence, given the different hypotheses, we note how we're drawing with replacement. So we simply multiply the probability of B1 given A times the probability of B2 given A. And similarly, here, the probability of B1 given not A times the probability of B2 given not A. And furthermore, we assume that the two hypotheses, A and not A, are equally likely to begin with. So what we have is, because on hypothesis A, all the marbles are black, the probability of drawing one, given it's black, is 1. So we multiply 1 by 1, which is the same as raising 1 to the power of 2. And then here we know the background probabilities in the two hypotheses, so we plug in 1/2 each, and then we simply do some math, and we get that the answer is 4/5. So given that we have drawn two black marbles, the probability that we're drawing from an urn of type A is 4/5, and that's what Bayes' theorem tells us. Now, if we do a third draw with replacement and it comes up black, what we do is we replace the squares here with cubes because we multiply 1 by 1 again itself. So we'd have B1 and B2 and B3 as a conjunction here. And because, again, all of the draws are independent, because we're assuming that we're drawing with replacement, we simply multiply the probability of each conjunct given the hypothesis. So again, if we took 3 draws which are black, we would simply be cubing the probability of a black marble given A. And furthermore, if we draw 10 black marbles in a row, we simply get the following. So here we raise 1, the probability of drawing a black marble, given that we're drawing from A, to the power of 10, because we multiply it by itself 10 times because there's 10 independent conjuncts. And similarly too, the alternative hypothesis, not A, if you remember, the alternative hypothesis was that there's an equal mix of black and white marbles. So for that, we simply multiply the probability of a black marble given that hypothesis, which is 1/2, times the amount of draws we've made. And so here's how we can use Bayes' theorem under these conditions to calculate the probability of some hypothesis or conclusion given a whole bunch of premises, a whole bunch of observations. We simply raise the conditional probabilities appropriately. And what we see then is that if we take 10 draws from an urn and they're all black, the probability that we're drawing from the A urn, i.e. the one in which is all black marbles, it gets very, very high as we draw more and more black marbles. So here we get very, very close to 1. So what we can ask is, can we conclude now that the argument A6 is strong to the degree of 0.999? So that is to say, this talk of marbles being black or white was a metaphor for talking about observing ravens and their color, because we were thinking about the observation of different ravens as draws from an urn, essentially, where the marbles were ravens and then their color was either black or some other color or white. So given the analogy, we saw that drawing 10 black marbles made it likely to the degree 0.999 that all the marbles were black. So the question is, can we therefore conclude that this argument, as we might use it in real life, is strong to the degree 0.999? And actually, there's two complications. And that is to say that if we're going to conclude that observing 10 ravens makes it 0.999 likely that all ravens are black, given this analogy, that depends on two assumptions which you might think are dubious. The first assumption is that we have to assume that the ravens we observe in real life are randomly sampled from nature's urn. That is, we have to assume that the observations are independent and unbiased. But that might not be true. If there are white ravens in the world, they might be limited to certain regions. So where we are living could make a big difference to what we find. So what that means is that the move from assuming that the probability of all this evidence given A is just multiplying the probability of each evidence given A by the other ones, that making that move requires the assumption that the evidence is independent of A. But that is a dubious assumption, and we can't make it in all cases. So in many cases, calculating this conditional probability is much more complicated than simply squaring or cubing or raising to the power of 10 or the amount of conjuncts we have. And when in the previous lecture, when we looked at how to solve problems with multiple conditions where we did not assume independence, that is how we'd start applying Bayes' theorem when we can't assume one. But there's another problem, which is that in this urn example, we assume that there's only two alternative hypotheses. We assume that either the urn contains only black marbles, or the urn contains an equal mix of black and white marbles. So that's like assuming that there's only two possibilities about ravens. That is, we would be assuming that either all ravens are black or half are black and half are white. So in order to draw an analogy with this urn case, we'd have to assume that there's only two possible hypotheses for the possible colors of ravens in this world, which is that either they're all black or half of them are black and half of them are white. But in real life, when we encounter a new species, we can't assume that these are the only two possibilities or hypotheses about the overall colors. It could be that, for instance, 90% of ravens are black, or maybe 31% are, or maybe 42.718%. Okay, so these are all possible hypotheses about the overall distribution of colors of ravens, which we're simply not taking into account when we did this simple urn example. Okay, so that's another issue for how to draw the analogy between our argument about ravens and this argument with the urn. Okay, so now I'll conclude this lecture and conclude the unit with giving a general version or a generalized version of Bayes' theorem, which allows us to take into account many different hypotheses, not just two. Okay, so where you have a large number, possibly a very large number of hypotheses where they are mutually exclusive, so each hypothesis has to be inconsistent with all the others. So these are a list of different, genuinely different hypotheses. So for instance, one would be that all ravens are black, the other is that 90% of ravens are black, the other is that 31%, etc. So where we have a bunch of mutually exclusive hypotheses, and where we assume that these hypotheses exhaust all the possibilities, okay? So these hypotheses are mutually exclusive and exhaustive. What we can say is for any one of these hypotheses, hi, so where I is between 1 and n, the probability of hi given some piece of evidence equals the probability of the evidence given hi times the prior probability of hi over, and then in the bottom, instead of just looking at, as in the examples above, where we had two hypotheses, we looked at the probability of the evidence given the hypothesis times the probability of the hypothesis versus the probability of the evidence given the negation of the hypothesis times the negation of the hypothesis, that one alternative. Instead of simply summing up these two products, what we have to do is we have to look at what all the different alternatives say about the evidence and how likely those alternatives are. So here's a very general version of Bayes' theorem, which lets us apply it to reasoning about evidence where we have a large number of alternative hypotheses. And so this concludes now our discussion of probability theory and how to think about inductive reasoning. And then next week we'll begin our short unit where we'll be building on our tools of thinking about probabilities in order to understand how to reason about making decisions under uncertainty.